In this video, we'll discuss the central limit theorem and how to find probabilities using the central limit theorem. The central limit theorem is the most important theorem to statistics as it allows us to perform inference based off the normal distribution. The central limit theorem says this: if we take a sample size of n where the n is greater than or equal to 30 are drawn from a population, and regardless of the shape of the population, this is one of the most important parts of it, regardless of that shape of the population, the sampling distribution of the sample mean, remember we call the sample mean x bar, will always be approximately normal. This n greater than 30 right here is called the sufficiently large condition. And here's what it allows us to do. Here's what it's going to help us set up. If we look at any mean where the n is greater than or equal to 30, it follows an approximately normal distribution with a mean of the population and a standard deviation of sigma divided by the square root of n. That's the central limit theorem. That's what we developed back in sampling distributions of those properties, where we saw that mu of x was equal to mu of x bar and sigma x bar was equal to sigma x over the square root of n. So what's where this is coming from. This also works if, so this sufficiently large condition doesn't have to be met if the distribution that we're drawing samples from, such as in our previous example, in sampling distribution where we had normal distribution, if the distribution you're drawing your samples from is normal, the sufficiently large condition doesn't have to be met. And so here's an example of what all this means. So we're going to find the mean and standard deviation for the following sampling distributions. Example 1 says cell phone bills for residents of a city following an approximate city have a mean of $47 and a standard deviation of $9. Random samples of 100 cell phone bills are drawn from the population. Find the mean and standard deviation of the sample mean sampling distribution. So first off, we need to check a couple of things. And the first thing we're going to check to see is if we're talking about the sample mean. Well, if you look here, it says find the mean and standard deviation of the sample mean sampling distribution. So we're talking about the sample mean. The other thing we're interested in is what is the sample size that was given to me? Well, the sample size that is given to me says random samples of 100 cell phone bills. That's the sample size. So your n here, n is equal to 100. Now, what is significant about 100 compared to what we're talking about? Well, this number, n, is greater than or equal to 30. And here's what we're going to say. By CLT, we're talking about the sample mean, again, x bar will follow an approximately normal distribution with a mean equal to that of the population. The mean of the population is $47. And a standard deviation, which is $9. We'll take the standard deviation and we'll divide it by the square root of the sample size, which is 100. And this is going to simplify to 9 divided by 10, which is just 0.90. So this is all we're working on right now. So all we're interested in is what is the central limit theorem going to say? Well, if n is bigger than 30, or in this case really is saying this, if you have any kind of sample size, you're going to check one of two things. That n has to be bigger than 30. In this case, it is. If you look at the next one, look at your n. Let's find our n and let's see if it's bigger than 30. Assume the training heart rates of all 20-year-old athletes are normally distributed with a mean of 135 beats per minute and a standard deviation of 18 beats per minute. Random samples of size 4 are drawn from the population, and the mean is determined for each. Find the mean and standard deviation of sampling distribution of sample means. So again, we're interested in the sampling distribution of sample means. However, we look at this time, my n is equal to size 4. So your n is 4. Well, that n is not bigger than 30, so n is less than or equal to 30 this time. So we can't use central limit theorem. But if we go back and read this again, here it tells me that they are normally distributed. So the population I'm pulling from is already normally distributed. And because of that, this n bigger than 30 condition right here does not have to be met. And we're going to say this now. X bar is approximately normal. The sample mean is approximately normal, having a mean with that of the population, which is 135 beats per minute, so that's 135, and a standard deviation of the population is 18, divided by the square root of the sample size, which is 4. And this is going to simplify to 18 divided by square root of 4, which is 2. So 18 divided by 2 is 9. Now, we're going to use these facts, and I want to cover how to find the standard deviation and the mean of a sampling means distribution right now. We're going to use these facts to find normal probabilities next in the next examples. So let's look at this example. And it says, in a survey of a company, the mean salary of employees is $29,321 with a standard deviation of $2,120. Consider a sample of 100 employees. Find the probability their mean salary will be less than $29,000. So here's how this works. What we're interested in is we're looking for a sample mean or a sampling distribution for the sample mean. And so we're going to try to find a mean first. Let's find out if they're talking about a mean. And you can see right here it says find the probability of their mean salary. So we are talking about a mean here. So because we're talking about that mean, we need to look for a couple things. Either the distribution needs to already be normal from which we're pulling from, or the n has to be greater than or equal to 30. Well, we can see, does it say anything about the distribution being normal? No. But we do have a sample of 100 employees right here. That means that my n is equal to 100, and because n is greater than or equal to 30, by CLT, I know that the mean salary, x bar, is going to follow an approximate normal distribution with a mean of the population, which is 29,321, and a standard deviation of 2120, the population standard deviation, divided by the square root of n, which is 100 in here. This value here is going to simplify to just 212. And now we've solved problems where we found probabilities from normal curves. And we know this is a normal curve because of the central limit theorem tells us it's going to be approximately normal. So we're going to draw a normal curve. And at the center of this curve sits what value? Well, it sits the mean, which is 29,321. They ask about the value of 100 employees that have a mean of less than 29,000. So less than 29,000 to the left of this value, sitting here. And less than would be shaded this way. Well, how do we find the probability under a normal curve? We're going to do normal CDF. Let's actually write the statement for this first. So the probability that your x value is less than or equal to 29,000 is equal to, in a calculator, you do normal CDF. What's the lower bound here? Well, we can see from the curve, the lower bound is negative infinity, or negative 99999. The upper bound is stopping at 29,000. We need a mean because we're not finding z-scores. So we know our mean, we can see that the mean is 29,321. And the only thing different about this problem is that now the standard deviation, instead of using this population standard deviation that was given to me, I actually have to divide by a sample size of 100 to get the actual standard deviation. And then here when we divided by 100, we got 212. So this will be 212. In a calculator, we do that. So let's do that. Second bar is normal CDF. 29321. I'm sorry, 29,000. 29321. And 212. When I do that, I get a value of 0.065. So there's a 6.5% chance we're going to get a value. If we look at 100 employees and find their sample mean, there's a 6.5% chance we're going to get a value of $29,000 for that mean or less. Let's look at one more example. The mean room and board expenses per year at a four-year college is $9,400. You randomly select 9 four-year colleges. What is the probability that the mean room and board is less than 9,126? Assume that the room and board expenses are normally distributed with a standard deviation of 1,500. So first, and again, we're trying to identify, we're talking about a mean. And we see that in the first part of the problem, it says the mean room and board. So we're definitely talking about a mean. Now, because we're talking about a mean, you're going to look for two things. Either the sample size has to be bigger than 30, or they tell you that it comes from a normal distribution. Well, our sample size here is we're looking at 9 of these four-year colleges. That's not bigger than 30. But if you keep reading, it tells you that boarding expenses are normally distributed. That's what we need to do this problem. And so what that tells me now is this. N is equal to 9, which is not 30. But because it's normally distributed already, by CLT, and you always use CLT when you have a sample size. Everything we've done so far has always been an N of 1, which wasn't a sample. So you always looked at an individual or a single item. Now you're looking at sample sizes, so groups of people when you do this, or groups of items when you do this. In this case, 9 colleges. By CLT, X bar follows a normal distribution with an with a mean of 9,400 and a standard deviation of 1,500 divided by the square root of 9, which is 1,500 divided by 3 are 500. So from this, what we do again is we draw a curve. The mean of the curve is going to sit at 9,400. We're interested in the value 9,126, and we want to see if it's less than that value. So again, shaded to the left. We want to find the probability that X is less than 9,126. So we'll do normal CDF because we're on a normal curve. We're trying to find probabilities. And the lower bound here is, again, negative 999. The upper bound is 9126. Your mean is 9400. And your standard deviation is 500. Second vars, normal CDF. Mean is 9126, 9400. And I get this equal to 0.2918. Notice here that this value is pretty likely to occur. That's because 9,126 isn't that far off from 9,400. The further you get away from this value, or this true value, 9,400, what happens to this value? It should decrease because you're moving closer and closer to the tails. And again, we use the central limit theorem when we're given the sample size. So if you see a sample size, whether it be 9 or whether it be 100, if you're looking at the sample size and you're looking for two things, you're looking for it to talk about a mean, and you're looking for a sample size that is either bigger than 30 or if it comes from a normal distribution.